Welcome to the YouTube classes. Dear students, after having the topic, which one previously we know done, force between two parallel current carrying conductors, we are having a topic torque on a current carrying coil in an uniform magnetic field. That means previously we have studied whenever a dipole has placed inside a uniform electric field, then that electric dipole experiences a torque. That torque is equal to what we have derived here means tau is equal to P sin theta we have derived, or tau bar is equal to P bar cross E bar. Okay, like that we have derived one expression. P is nothing but electric dipole moment, E is nothing but electric field, tau is nothing but torque. Torque is nothing but turning effect or rotating effect. Now, whenever a current carrying coil is placed in a uniform magnetic field, inside a uniform magnetic field, if you place a current carrying coil means coils means we can take coil in the shape of circular, in the shape of square, or in the shape of rectangle also we can take. Is it any type of coil? Circular current carrying coil, otherwise square current carrying coil, otherwise rectangular current carrying coil also we can take. Now, whenever a current carrying coil has placed inside a uniform magnetic field, then that coil is having the turning effect. What kind of effect? Turning effect. For example, if you take, this is a rectangular coil. If this rectangular coil, whenever it is placed inside a magnetic field, immediately this coil will get the turning effect, rotating effect like this. Like this you can get the rotating effect. Is it? Now, what is the torque? Suppose if the dipole has placed in electric field, the torque formula we got here. Suppose if this one magnetic field, inside a magnetic field, if you place a current carrying coil, how it can get the magnetic field? Okay, let me see here. Now, very first one, here I have taken two poles. This is the bar magnet, north pole of the bar magnet. This is the south pole of the bar magnet. Okay, in between the south and north pole of the bar magnet, here A, B, C, D. A, B, C, D is a coil, rectangular shaped coil. Now, this rectangular shaped coil is having whose length is nothing but, of course, we can take it as just to see whose length or breadth. See, breadth is nothing but A, we can take it as, and its length is nothing but what we can take it as, B we can take it as. This is the length. AB is length, BC is nothing but the breadth of the coil. Which is the coil? A, B, C, D is the current carrying coil. Now, the situation is being like this. At the same time, here the ends of the coil is connected here. Now, whatever the color is there, pink color, in pink color, whatever the two rings are there, these rings are called here slip rings. That means on these rings, wire is slipping easily. Now, here in green color, that means whatever the brushes are there, these two are said to be here carbon brushes. Right? Now, this one is nothing but here coil, current carrying rectangular coil is there. Now, this is the battery positive, battery negative. So, battery positive has connected here means from here current is begins to flow. How much amount of current is flowing in the circuit? I amount of current is flowing in the circuit. Okay, like this. A to B, B to C, C to D, and D to A. It will be like this. Keep on. Is it? Now, here north and south poles. In between north and south poles, what I have placed here means I have placed here coil. Okay, what is the necessity here? Taking the north and south poles means necessity to take the north and south poles here is nothing but, okay, these two poles are produces the uniform magnetic field. What is the direction of the magnetic field in case of poles from north to south? What is the direction of magnetic field? North to south. See, north to south means, okay, I can show here like this. Now this is the direction of magnetic field, that is B bar or B also. Now this is the direction north to south. This is the direction of magnetic field. See, now this direction of magnetic field is exactly parallel to the BC and parallel to the AB. Is it? Right. Next, thereafter, here coil is begins to rotate. Is it? Now for the rotation, here one axis is there. About any one axis only, okay, any body can be rotated. Now this is nothing but here dotted lines which I have shown. Okay, these dotted lines are nothing but here axis of rotation. Axis of rotation. About this axis of rotation, here coil is going to rotate. That means coil is going to rotate either like this or, okay, either like this or like this. Let me see. Now, very first see, here north and south poles are providing uniform magnetic field. Inside this uniform magnetic field, there is an arrangement of the current carrying coil A, B, C. Current is flowing from A to B, B to C, C to D, and D to A. The arrangement is being like this. Okay, right. Now, sir, how the magnetic field has going to generate here? Okay, let me see here. Now, very first point, when you are going to study this one, very first point. First, whenever the current carrying conductor has, that means in between these two poles, okay, in this complete area, what is there? Magnetic field is there. The direction of the magnetic field is being like this. Sir, whenever inside a magnetic field, this is the magnetic field, here completely magnetic field is there. Right, in between north and south poles, magnetic field is there. Right, sir, in a magnetic field, if you place a current carrying conductor, then that current carrying conductor experiences a force. Is it? That means in this one, totally how many conductors are there in coil? 4 conductors. A to B, one conductor, B to C, another conductor, C to D. Okay, next one, and D to A. Sir, whenever the current carrying conductor has placed in the magnetic field, okay, what it experiences means it experiences a force. Okay, that force is nothing but will sin theta. Will sin theta. We have derived the expression also. Whenever the current carrying conductor has placed inside a magnetic field, it experiences a force. That force is nothing but will sin theta. Now from this one, okay, let me see here how to. Okay, will sin theta means how to see to that there is a, okay, direction of the force and so on. So everything let me see. Now very first one, okay, you take it here, A, B. There are 4 arms are there, ARMS arms. 4 arms are there in this coil. Arm A, AB, arm BC, arm CD, arm AD. Right. In every case, what is the force? Okay, let me see. First here, okay, what I would like to write here means, okay, force on arm AB. Force on arm AB. Force on arm AB means, okay, first I am taking here AB I am taking. Okay, that force equal to what I can take? A force F1 I can take. F1 is equal to, what is the formula? Bill. Okay, bill. L means length of the conductor. But here A to B, what is the length is there? Length is nothing but small b. So small b, of course I can take, that is nothing but sin theta. Okay, now from this one here BIB into sin theta value is nothing but 1 if you take it means, okay, why it is 1? That is nothing but since theta is equal to how many degrees? 90 degrees. What is the theta equal to 90 degree? Means, okay, angle between the current and magnetic field both are perpendicular. See, you are observing here, this is nothing but direction of magnetic field. Now this is nothing but current carrying, right? How these two are there? Current is flowing like this and magnetic field is being like this. Both are perpendicular to each other. Because of this reason, theta is nothing but 90 degree. So force on first arm is nothing but what I can write? F1 is equal to BIB. Of course, I can BIB. Okay, fine. Sir, force is nothing but BIB. You are saying BIB, right? What is the direction of force? Force direction, if you wanted to tell, means we have to use the Fleming's left hand rule. What is the Fleming's left hand rule? If the in a left hand, if the first three fingers are arranged mutually perpendicular to each other like this, in which middle finger is gives the direction of current and forefinger is gives the direction of magnetic field and this thumb is gives the direction of force. Is it? Now I am arranging here. Now this is nothing but the direction of the magnetic field. Is it? Now direction of the magnetic field. This one is nothing but direction of the current. Direction of the magnetic field is current. Now middle finger, direction of the current is in which direction? Downward direction is there here. Middle finger is pointing downward direction, but actually current is in which direction? Current is in, okay, upward direction. So this one you just rotate like this. You just rotate. Now I am rotating like this. Now see, this is the direction of magnetic field and this one is nothing but upward direction. Upward direction, what is there? Upward direction, current is there, that is nothing but I current is there. Now thumb is pointing in which direction? Inward direction. Inward direction means force is acting in which direction? Inward to the board. So here force direction is nothing but what we can write now? Force direction is nothing but inward direction. Okay, force is nothing but inward direction. Okay, inward direction. Okay, so here force direction is inward. That is nothing but here I am taking F1. F1 direction is inward. Okay, fine. Next one. Force on. Force on arm B. Force on arm BC. Right? Arm BC means on this one. What is the force? Let me see. Force on arm BC is nothing but F2. F2 is equal to L. L means length. What is the length of the BC conductor? Is nothing but A. So A you take it here. A into sin theta. That means here instead of sin theta, that means you make it here. That means in all cases current is perpendicular to the direction of the current carrying current always is perpendicular to the direction of magnetic field. Is it? Now here this is nothing but BIL. Sir, what is the direction of the this current carrying conductor? That means what is the force experienced by the BC? BC force experienced is nothing but BIA, of course. Similarly, BIA. Sir, BIA, okay, fine. Then, sir, what is the direction of force? Means here we are unable to place this one. Why? Because actually here the force direction is nothing but inward direction. Here it is there like this, inward direction. Inward means downward direction. That means here on BC the force is acting in which direction? Means downward. In the downward direction, what will be axis? Force will be axis. That is downward direction. Fine. Next, here you just see force on another arm. Third arm is there. Force on arm. AB is over, BC is over. So CD. What is the force on? CD. Force on CD is nothing but just see. Right. Force on CD is nothing but let me take F3. F3 is equal to Bill sin theta. BI. That means what is the length of the CD? Length of the CD is equivalent to small b. Small b. BIB. Small b. Sir, what is the direction of the force? Here there is a possibility to apply the Fleming's left hand rule here itself. Now here this is nothing but direction of magnetic field. Middle finger is pointing the direction of current. So magnetic field direction current and field direction also correct. So what is the direction of the force? Direction of the force is pointing by the thumb. So the direction of the force is nothing but outward direction. We can take it as like this. Now this is nothing but inward direction. Okay, here it is nothing but outward direction. Right. Next, this force is nothing but here F2. Here the force F2 is acting downward direction. F3 is outward. So this is nothing but force on CD. Force on arm CD is nothing but F3. Okay, on this one, whatever the force is acting, that force is nothing but F3. That F3 is acting in which direction means, of course, that is nothing but outward from the board. From the board. Okay, right. Now this force is inward to the board. This force is outward to the board. Next one. Thereafter, if you just see, what is the force? Force on arm DA. Arm DA. That means that force is nothing but F4. F4 equal to BI. Okay. D to A. What is the length? Length is nothing but A. So I can take. Sir, here if you apply this one means, okay, this force is acting in which direction means upward direction. This force is acting in which direction means upward direction like this. So force F4 is acting on which direction means upward direction, that is nothing but F4. Yes, right. Next one. Thereafter, that means upward direction. Now this is downward, one is downward, other one is nothing but upward direction. Yes, listen. Alright, from the diagram, whether you know or not, F1, F2 and F4 both are equal in magnitude, opposite. So F1 and F2 and F4 both are cancelled with each other. You just see, okay. Therefore, F2 and F4 are equal and opposite. That means F2 is acting downward direction, F4 is acting upward direction. Okay, opposite. Hence they cancel with each other. They cancel with each other. They cancel with each other. Okay. Right. Next one. What about the F2 and F4 are? What about the F1 and F2? F1 and F3. F1 and F3, two forces are acting as a couple. Couple means two forces are equal in magnitude and opposite in direction. Acting at two different points. One is at one end, other force is at other end. So here F1 and F3 act like couple force. Act like couple. That means these two, F1 and F2, both are acts like a couple. Couple means two forces are acting at two different points from the axis of rotation. Now this is nothing but, you just observe here. Now from here to here, see, this is nothing but 2 points. At these 2 points, two forces are acting. Now I am going to draw this one. At this point, you just see. Now this is nothing but first force. Okay, here it is acting. Here this one is nothing but F3 force is acting. Now this is F1 force is acting. F force is acting in inward direction. F2 force is acting. F3 force is acting outward direction. Now of course the center point, whatever there is there. Now this is nothing but center point. Now what is the total length from here to here? Here to here, F1 to F2, the length is nothing but A. So length is nothing but A means here to here, the length is A by 2, and here to here, the length is nothing but A by 2. That means if the two forces are are acting on a same line, okay, in different directions, equal in magnitude in different directions, then those two forces are said to be here couple. Couple forces are, okay, produces the turning effect on the body. That means if you take a tap of the bottle, while you are rotating the tap of the bottle, that means with this finger and these fingers, you are applying the force in opposite direction at two ends. Because of that only there is a rotation in cap. Is it? Now in similar way, here also it will be happen. Now thereafter, here you just see the torque on coil is torque on coil means torque equal to, what is the formula? Torque equal to formula is nothing but force and perpendicular distance. The product of force and perpendicular distance. Sir, torque is denoted by which letter? Torque is denoted by a letter tau. Tau is equal to this is the tau is equal to force means here F you take it. Since F1 is equal to F3 is equal to F. That means torque is equal to the product of either of the force. Both forces are equal in magnitude, opposite in directions. So F into perpendicular distance. Perpendicular distance from the axis of rotation or center point. What is the perpendicular distance from center point? Is nothing but A by 2 if you take. Right now from this one, tau is equal to force. Force means either F or F3. What is the force value we got here? That is BIB or F1 and F3. Both you see BIB. So here I can take BIB into A by 2 I can take. Now this is nothing but force. Of course we can take it as force. Just to see, right, just to see, actually net force means total force we have to take here. Net force we have to take. Net force is nothing but two forces. That means force is nothing but F1 plus F2 into perpendicular distance is nothing but A by 2. Right, F1 and F3. Right, F1 is nothing but BIB plus F3 also BIB into A divided by 2 we can take. Right, next tau is equal to BIB plus BIB 2BIB into A divided by 2. Right, just look at here, 2 cancel. So what is the remaining here? Tau is equal to B into I. Next this is nothing but B. B is nothing but one of the length of the coil. A is nothing but other length. Length into length is nothing but area. Okay, since you write here in bracket, okay, what I can write? See here, A is equal to B into A. Area is equal to B into A. Next here I got here torque is equal to tau is equal to I got BIA. But here we know that here. What is that? We know that magnetic dipole moment I is equal to, we can write the product of current into area. That means instead of product into current, product of current into area. What I can write? I can write here M. So torque tau is equal to what I get means MB. I mean torque tau is equal to MB. Torque tau is equal to MB means here I can write this is MB. I can write M is nothing but magnetic dipole moment. M is nothing but magnetic field. Is it? Of course, in vector form. How we can write? In vector form. In vector form. Why? Because torque is a vector quantity. Tau bar is equal to M bar cross B bar. M bar cross B bar. Now this is nothing but this. Okay, right. Next to M bar cross. That means A bar cross B bar. This is not necessary. See, torque equal to P bar cross C bar. P bar is nothing but electric dipole moment. M bar is nothing but magnetic dipole moment. E bar is nothing but electric field. E bar is nothing but magnetic field. Same we got. Right. Now thereafter here A bar cross B bar means what I can write means A bar cross B bar is equal to AB sin theta. In similar way, okay, tau is equal to what I can write means tau is equal to MB sin theta. We can write MB sin theta also we can write. Now tau is equal to this is correct and this is also correct. This is at any arbitrary angle of the coil, at any other angle between M bar and B bar, andre what I am saying here means magnetic dipole moment ಮತ್ತೆ magnetic field ಮಧ್ಯದಲ್ಲಿ other than 90 degree angle ಇದ್ದಾಗ ಯಾವ ತರ ಇರುತ್ತೆ ಅಂದ್ರೆ ಈ ತರ ಬರುತ್ತೆ. Yes, this is the important concept. Yes, make it. Now this is about torque on a current carrying coil in an uniform magnetic field. Yes, torque means force into perpendicular distance. Force is nothing but net force. That means how many forces are acting? Those two forces we have. Yes. Right. After having the previous topic, torque on a current carrying coil, there is some another topic is there. What is that means? Magnetic dipole moment of a revolving electron. That means a revolving electron is having the magnetic dipole moment. How it is? Let me see. Now, see, this is nothing but the situation I am taking. The situation I am taking. This is nothing but orbit of the electron, here in which at the center, see, there is a positively charged nucleus, right? That positively charged nucleus is nothing but Ze, right? From this one, from the center of the nucleus at a distance or radius r, here one electron is revolving in a circular path. The charge of the electron is nothing but E minus. Of course, this electron is moving with a velocity. Is nothing but how much more? Moving with a velocity that is nothing but v in this orbit. Is it? Now, according to the Bohr's law, right? Bohr's atom model already you have studied in atoms chapter. According to the Bohr's atom model, electron is revolving around the positively charged nucleus in a particular orbit. Is it? The radius of the orbit is nothing but r. The charge of the nucleus is Ze, right? Velocity of the electron in that orbital is v, and the charge of the electron is E minus E. This is right. Thereafter, what is the time period of the electron for a complete revolution? That is nothing but capital T. Also, we can take. Of course, here electron is performing the circular motion. Moving electron is nothing but gives the current. Is it? Moving electron is gives the current. In similar way, here rotating electron also gives the current. Right? The current due to revolving electron. The current due to revolving electron. I is equal to what I can write? Current equal to charge by time. Charge is nothing but minus E, charge of the electron, and time is nothing but capital T. Where T is nothing but, right, look at it. Where capital T is period of revolution. Period of revolution of electron. That means the time taken by the electron to complete one revolution is nothing but T. Of course, T is equal to T equal to what is? Time equal to distance by speed. Distance means what is the total distance covered by this electron in a complete revolution? That is nothing but 2 pi r. There r is nothing but radius of the orbit, circular orbit. divided by v. V is nothing but speed of the electron in that orbit. Now from this one, okay, we have C. Current I is equal to charge minus E divided by T. T means what? I can write 2 pi V. 2 pi R divided by V. Now this one minus EV divided by 2 pi R. Of course, now this is nothing but current. That means what is the current, okay, which can produce the electron when it is moving in a circular path, means that is I equal to EV divided by 2 pi R. V is the speed of the electron in circular orbit, R is the radius of the electron. Next one, afterwards, we just see here, right? But from the magnetic dipole moment, is what is the magnetic dipole moment formula? Magnetic dipole moment formula is nothing but M is equal, actually magnetic dipole moment means for electron, see, I am representing with mu L. Mu L is nothing but magnetic dipole moment. Mu is magnetic, not M. Mu is equal to the product of what I can write current into area. Right? Here current is nothing but, what is the current value I got here? Current is nothing but minus EV divided by 2 pi R into area. What is the area of the current carrying coil? Is nothing but pi R square. So pi R square again. So here R square, R cancel, pi cancel. So mu L is equal to magnetic dipole moment of current carrying electron is nothing but minus EV into R divided by 2I. Is it? Now thereafter, here we are having mu L is equal to minus EVR divided by 2 is there. Now for this one, you multiply and divide the mass of electron. With the mass of electron, you multiply it. With the mass of electron, you just divide it. And thereafter, here mu L is equal to what I got? Okay, that is nothing but minus E into here ME, mass of electron, into VR divided by 2 mass of electron. MVR means mu L is equal to what I can write? E minus E divided by 2ME into L bar I can write, where this is mu bar. L bar is nothing but angular momentum. Angular momentum formula is nothing but, what is the angular momentum formula? L is equal to mvr. So mvr is equal to L. Now this is the magnetic dipole moment of revolving electron in terms of angular momentum. Magnetic dipole momentum of electron, revolving electron in terms of angular momentum. Right? Suppose if you take the ratio of these two, what is that? Mu L divided by L is equal to, I can write E divided by 2M again. Now the ratio of magnetic dipole moment and the angular momentum, the ratio of these two is called here gyromagnetic ratio. Where? Look at here, the ratio between these two. Where? Mu L divided by L is called gyromagnetic ratio. Right? How to define the gyromagnetic ratio? I have given in notes. Right? Mu by L, capital L. This is right. Mu by capital L. Right? The ratio of magnetic dipole moment to angular moment is called here gyromagnetic ratio. Now it is constant. Gyromagnetic ratio value is constant. What is the value of mu L divided by L? Is nothing but 8.8 into 10 power. 8.8 into 10 power 6 coulomb per kg. Coulomb per kg is nothing but ferromagnetic ratio. Is it? Now this one actually we have to discuss in this topic. Afterwards, from the Bohr's second postulate, Bohr's three postulates are there. Second postulate is related to the angular momentum. Right. Next, look at here from Bohr's second postulate. What we can write? Angular momentum L is equal to NH by 2 pi we can write, where N is integer. That means N values are equal to 1, 2, okay, 3 and so on we can write. H is nothing but Planck's constant. We know that the Planck's constant value is 6.625 into 10 power minus 34 joules second. Is it? Now, from this one, this is nothing but if you take it, equation number 1, equation 1 becomes, how we can write equation 1 means, equation 1, mu L is equal to minus E divided by 2 into mass of electron. Thereafter L, instead of L, we can write NH divided by 2 pi. So mu L is equal to, here we can write N minus NEH divided by 2 2s of 4 into pi into mass of electron also we can write. Now this is nothing but magnetic dipole moment of electron in terms of Planck's constant. Is it? Thereafter, you just see, if you take N is equal to 1, N is equal to 1 if you take it. If you take it, N is equal to 1. If you take it, N is equal to 1, then mu L value becomes minus EH divided by 4 pi into ME. We can take. That means it is called. That means when you take N is equal to 1 in this equation, so whatever the value we are getting here, this value is equivalent to mu B. Mu B is nothing but here Bohr magneton. Right. Now is nothing but mu B is Bohr's magneton. What is the Bohr's magneton? Suppose if you take in magnetic dipole moment, when the electron is revolving, okay, if you take first orbit, if you take the value of angular momentum, whatever the magnetic dipole momentum of electron while it is revolving in first orbit is called here Bohr's magneton. It's called here Bohr's magneton. What is the value of Bohr's magneton? Here means mu B is equal to 9.27 into 10 power minus 24 ampere meter square. Now Bohr magneton also it is a magnetic dipole momentum only. But while you are taking N is equal to 1. N is equal to 1 if you take it, suppose, okay, this one is nothing but we can take. See here, sir, revolving electron is having magnetic dipole moment. Of course it is having. Why? Because current carrying loop is nothing but acts as a magnetic dipole. Current carrying loop is acts as a dipole, magnetic dipole. Right here, electron while it is revolving around the circular path, electron is moving means, okay, around this path, what is their current is flowing. Now around this current carrying, that means circular path is behaves like here magnetic coil. That means current carrying coil. Now this current carrying coil is having the magnetic dipole moment. That magnetic dipole moment we have written in two forms. This is one form in terms of angular momentum. This is in terms of Planck constant. Right here, what is the Bohr magnetron? This is the important. Bohr magnetron is nothing but the first orbit. The Bohr magnetron is the magnetic momentum of the revolving electron in which orbit? First orbit. See, what is the gyromagnetic ratio? Important. Right, what is the gyromagnetic ratio? The ratio of magnetic dipole moment to angular momentum. the ratio of magnetic dipole momentum of electron to angular momentum of electron. Here negative sign is there here. This negative sign is indicates negative sign is indicates what it indicates means mu L means magnetic dipole moment. Magnetic dipole moment is opposite to angular momentum. That means angular momentum and magnetic dipole momentum of electron both are opposite to each other when the electron is revolving in circular path. Yes, simple concept formulas and definitions are important. Derivation is not that much important. Now this formula and concept is important. Okay, right. Make it.